Hi, and welcome to another lesson in the physics video series. We are going to study elastic forces and potential energy and extend that concept into simple harmonic motion. In the last video, we studied Hooke's law and the spring constant. We even extended the concept to include the potential energy stored in a spring when it was elongated. Now we're going to extend the concept even further to talk about the recoil of the spring and the oscillation that takes place when it bounces back and forth. Alright, let's get started. Let's answer this question. What is simple harmonic motion in physics? Quite simply, simple harmonic motion is the repetitive back and forth movement across a central line or equilibrium position so that the maximum displacement, the stretch, on one side of this line is equal to the maximum displacement on the other side of this line. Recall this diagram from the notes. We're going to take this diagram and set it into motion in a simulation. What we have here is a mass on a spring, and this dashed line is the equilibrium position. Then I apply a force and I stretch the spring by pulling the mass, say, to the right a certain distance x. Automatically you can see force times distance. That's the work invested into stretching this spring. That's a potential energy. Then, of course, you remember from the last video that Hooke's law is the restoring force. That's the force that's pulling equal and opposite to my applied force, which will return it back towards the equilibrium position. However, once it passes the equilibrium position, it has developed kinetic energy. The spring recoils and sets this mass into motion. So at this point, it has no speed. And of course, if it has no speed, it has no kinetic energy. Then, as it returns towards the equilibrium position, it's gaining speed. And as it's gaining speed, that is a gain in kinetic energy. Where does it get that kinetic energy from? It gets it from the stored potential energy it had at the fullest extension. Well, inertia will continue to carry the spring back across the dashed line until it goes the equal distance delta x on the other side, till it slows to a stop and then rebounds again. And if there's no friction, this will just keep going back and forth. Like I said, this is a static picture. Let's take a look at this in action in a simulation. Here I have a simple harmonic motion mass on a spring simulation. If I was to take this mass connected to this spring and stretch it to a distance, in this case 5 centimeters, I pull back, that is the extension distance. This spring will want to restore the mass when it's moved over here back to the original position, x equals 0. But because it has gained velocity and therefore kinetic energy and therefore momentum, it will continue past the initial point on the equilibrium position and will continue to the left side of the equilibrium line. Let's take a look as I run the simulation. Here's the extension, and there's the recoil. And there it goes back and forth. So what we're going to do is focus on the line of the edge of this mass with its position for the x max, 0, and x minimum. Here's maximum. Now it recoils and it goes to the center point, the equilibrium point, and it's gaining that speed, and it has the momentum which carries it past it until it gets to the left side where it begins compressing the spring, and then Hooke's law works in the opposite direction. Since the spring is now compressed, Hooke's law will work to extend the spring and it'll push it away. The mass will be then pushed to the right. As you can see it back and forth. Now, let's take a look at the same scenario, except in the vertical direction. Let's take this 100-gram mass and attach it to the bottom of the spring. As you can see here, the 100-gram mass is cut by this black dashed line, which is the equilibrium line. Now, I've created a movable line, this little red dashed line, which will show you that when I withdraw the spring, I pull down on it, and it stretches. I bring the mass to the red line. When I release it, the restoring force will cause the mass to oscillate. Up, down. And here we have restored back to the equilibrium position. I will now run the simulation again, but this time I will draw your attention to the energy graph. Here you will see the changes in potential and kinetic energy. When I withdraw this mass and pull it down to a certain fixed elongation distance, you can see that the potential energy has risen to a maximum value. When I release the mass, the spring will recoil and this mass will begin to accelerate towards the equilibrium position. It will gain speed and therefore gain kinetic energy. When it reaches the extreme opposite point, as you can see here, the 100-gram mass is the same distance above the dashed equilibrium line as it was below, it comes to a stop. All of the kinetic energy is reconverted into potential energy as the spring is now compressed. Hooke's law wants to restore the spring back to its original natural length, which was somewhere down here, and it will now push this mass away. As I run the simulation and continue it, you can see the oscillation down, then up. And as this is happening, let's take a look at the energy bars. Potential is converted to kinetic, and kinetic is reconverted back to potential. And this would go on indefinitely if there was no friction. Of course, if there was friction, then the oscillation would damp out or simply decay, and each bounce would be lower and lower from where it was in the previous bounce. Kind of like if you bounced a basketball, it would do a few bounces until it just stopped. All right, let's take a look now at some oscillation facts. The time it takes to go back and forth is called the period of oscillation of the simple harmonic motion. The time period t is given as 2 pi square root mass divided by spring constant k. So, when a spring is elongated and released, the mass will oscillate continuously, of course without friction, and it converts potential energy to kinetic energy and kinetic energy back to potential over and over again. If the spring is vertical, the action force is the weight of the mass. Nevertheless, whether it's horizontal or vertical, the mass will have a period of oscillation given with the following formula: T equals 2 pi root m over k. Let's take a moment and analyze this formula T equals 2 pi root m over k. What I've done here is set up a calculator with values. I'm letting the mass be 1 in each one of these computations. And then I'm going to change the k from 1 to 2 to 3 to 4. And let's take a look at what happens to the period of oscillation as the spring constant increases. As you can see here, when k's value is 1, we have a 6.28 second period. And then, of course, when the k value increases to 2, we have a 4.4 second period. And then when the k value is 3, we have 3.62. And then when k value is 4, we drop all the way down to 3.14. So you could see that the general trend is that when k value in this formula increases, the period of oscillation decreases. So the higher k value means a tighter spring. It requires more force to stretch it. But also, when you do stretch it, that force is stronger and causes a greater acceleration. So the time it takes to return or restore back to the equilibrium position is less. Let's run the simulation and make that observation that when you increase the spring constant, you're going to see a change in the period of oscillation. We're going to start with a small spring constant, and we're going to begin by releasing the mass, and you can see how slowly this mass oscillated. We'll increase the spring constant. You could see the spring picture got thicker. We'll run it again. You could see that the oscillation is now faster. We will increase it again, and you can see that it is even faster. And finally, let's just make it as large as it can go, and you can see how quickly the oscillation goes. Now let's take a look at a variation. Instead of varying k, let's look at the variation of the mass. We're going to keep k as a value, and we're going to make it 1 in each one of these equations. We're going to raise the mass from 1 to 2 to 3 to 4. Let's take a look at what happens to the period of time as the mass increases. So starting with a basic mass of 1, we have a time of 6.28 seconds. But if we double the mass, we go from 1 to 2, we can see that the period of oscillation rises to 8.8 seconds. If we triple the mass and we go to 10.88 seconds, and if we quadruple this mass, we are now at 12.5 seconds. So the general trend is that as the mass increases, the period of oscillation also increases. It's not a perfect linear increase, but it is definitely an increase nonetheless. And finally, let's run the simulation again and show that as we keep the spring constant the same, the heavier we make the mass, the slower the oscillation will be. Let's watch with 50 grams. It's a very rapid oscillation. Now I'll increase the mass, say to about 100. And you could see automatically that it has slowed down. It's taking longer to bounce up and down. Let's increase a little more, say to around 150. Much slower. And finally, let's just go for it all. 300. Very slow. We increased the mass. We retained the spring constant. And this matches our numerical findings. This brings us to the conclusion of our lesson of simple harmonic motion. We can see that the potential energy stored in the spring is converted back to kinetic energy and back to potential and back to kinetic indefinitely if there's no friction. And we also learned that the period of oscillation is governed by this formula T equals 2 pi root m over k. I hope you enjoyed this lesson, and I look forward to seeing you in the next video where we will be discussing the simple harmonic motion associated with the pendulum. Everything you learned here will be immediately applicable there. Thank you for watching, and we'll see you there.